Okay, this is going to be the first of 2 units on learning theory. And learning theory often begins with a discussion of the no free lunch theorem. So I'm going to start there. Let's talk about the no free lunch theorem. So this is what I often refer to as the Chomsky-Hinton axis. So Chomsky firmly believes that there must be some innate human knowledge of the possible grammars of natural language. Because without some innate knowledge of the possible grammars of human language, there's no way we could learn to judge grammaticality on sentences we've never seen before. On the other hand, Hinton believes that there's some more universal learning algorithm, a learning algorithm that is so general that it can learn anything essentially from any domain, including language and other areas. And I'm going to try to defend Hinton's position. I think these days Hinton is kind of winning. But let's first look at the Chomsky argument, or the argument that learning theorists often present. So learning theorists say, well, you can't generalize without bias. So what does that mean? It means if I've got a bunch of XY pairs in my training data, and I see a new X that I've never seen before, I have to have some constraint on the space of possible functions that allows me to constrain what the value of X is on this new input. Without some constraint or bias on the space of functions, prediction is impossible. So let's look at that argument a little more carefully. So the argument says, what does it mean to have no knowledge about what the function space is? Well, one interpretation is you pick uniformly from the space of all possible functions. So if I pick uniformly from the space of all possible functions, it's a theorem that with high probability, I get a random function. What do I mean by a random function? I mean a function that cannot be compressed by a rule with a small number of bits, smaller than the data itself. If you say, well, I can't learn if I have no information, what that's really saying is you can't learn a random function. And of course you can't learn a random function. So let's look at what I'm going to call the free lunch argument. I'm going to consider a programming language like C++ or Python, Python NumPy, and I'm going to even allow an arbitrarily large standard library of functions you can call. And what I'm going to look at is if I've got a rule, predictive rule for predicting Y from X, and I write it in this language, how simple is it? How many bits does it take to name it? Now, this goes back to Occam, right? Occam said that if you have a rule that works or a theory, and the theory is simple, right? And its simplicity can be interpreted as how many bits does it take to name it, that a simple theory that does well on your experience, on your training data, will generalize. So we prefer simple theories. So I'm thinking about simplicity as just the number of bits it takes to name the rule in a language like C++ or Python with a very large lemma library. And so I'm only charging for the number of bits for the program. I'm not charging for the number of bits in the standard lemma library. The program just calls the standard lemma library. Okay. So let's state this free lunch theorem precisely. This is a true theorem. So I'm going to consider a loss function given a predictive rule and an XY pair. This assigns a loss. So if this rule is just predicting Y from X, the loss would be 1 if it gets it wrong and 0 if it gets it right. And that loss is clearly between 0 and 1. But we want to consider other losses that with other maximum possible losses. This is the maximum possible loss. And we're going to need that in the theorem. We need the loss to be bounded. Okay, so I can define the loss of a predictive rule to be the average over the population of its loss when I draw from the population. This is like the generalization error, the test error. It's over the population. A given rule also has a loss on the training data. It's an average over the training data, an expectation over drawing from the training data of the loss on the XY pair in the training data. And the whole idea, the whole issue in overfitting is that the loss on the training data can be smaller than the loss on the generalization data, on the true population, the test data. And we want to know under what conditions can we provide a guarantee on the generalization loss in terms of the training loss. Okay, so now we're going to state a theorem, a true theorem. And this theorem is going to say with high probability over the draw of the training data. So we're assuming that the training data is drawn IID from a population distribution. And this is going to say with high probability over the draw of the training data, it's going to be true, this statement is going to be true simultaneously for all rules. So this is a statement that's going to hold for all rules F written in our language. So this is a hugely, enormously infinite set. It's right, all programs that you can write in your language, all programs. So it's going to be true for all programs simultaneously. With high probability, every program is going to satisfy this bound. So this bound says that the generalization loss is no larger than a number near 1, 10/9, times its training loss, plus a penalty that depends on the number of bits it takes to write the program. So this penalty is going to be smaller for small programs. As the training set gets bigger, this penalty is also going to go down. So if it's correct on a larger training set, the penalty goes down. This penalty, this is a number of bits. We defined it to be the number of bits it takes to name F. If I multiply by log 2, I get that in nats. And the theorem is going to want to use nats there. And then there's a part of the penalty that depends on how confident we want to be. So if we want this to be 1 in 1,000, then this is like 10 bits. But this is going to be many more than 10 bits. So this tends to completely dominate this sum. Okay, so this is providing a guarantee on the generalization error in terms of the training error or loss, generalization loss, training loss, plus a penalty in terms of the number of bits it takes to write the rule. Okay, so I'm gonna prove this theorem, and to prove this theorem, I need to convert from the number of bits it takes to write the rule to a probability distribution over the programs. So if you consider a stochastic process that generates 1 bit of the program at a time at random with 50-50 chance of each value of the bit, the probability that it generates exactly this program is 2 to the minus the number of bits it has to generate. So this is the probability of a program can be assigned. A program can be assigned a probability which is 2 to the minus number of bits it takes in the code for the program. Or that's equivalent to saying that the number of bits it takes to code the program is minus log 2 the probability. So we've seen in information theory that a probability distribution corresponds to a code roughly satisfying this. But now I'm not in. So what I'm going to do now is switch from thinking about actual codes. I'm going to forget about the codes, and I'm just going to talk about a probability distribution. But pointing out that there exists a probability distribution that exactly makes this true. So we're going to fix this probability. And now we can restate the theorem, exactly the same theorem. We restate it as saying the generalization loss is bounded by a penalty in terms of the log probability instead of the code length. It's exactly the same, except we're working with probability rather than code length. Now, before I go and prove the theorem, now that we're talking about probability, I want to compare the algorithm that comes out of this theorem with maximum a posteriori inference done in the Bayesian setting. So I'm going to compare the Occam generalization guarantee approach to learning to the Bayesian maximum a posteriori approach to learning. So if I want to find the H that provides the tightest guarantee on its generalization loss, which is a natural thing I want to do, then I just minimize this expression over H. And minimizing this over H, it turns out that this penalty doesn't depend on H, so it's exactly minimizing this expression. Now, we did the Bayesian analysis in the last unit or last couple units, And the Bayesian analysis starts by saying we're going to find the rule with the maximum a posteriori probability that maximizes the probability of H given the training data, where we have some prior distribution on the rule, some prior probability on H, which is analogous to this, and where we're assuming that the training data was actually generated from some rule that's drawn from that prior. And I'm not going to go through the derivation again, but we showed last time that that H star defined this way is equivalent to minimizing over H the log loss of the probability of the standard cross entropy loss of H on the training data, plus 1 over the training size times minus log the prior probability of H. Now, I should have said that this analysis here depends on a particular loss function, right? I'm saying in this Bayesian analysis, I'm taking the loss to be the log loss, the cross entropy loss. In order for this theorem to hold, I need my loss to be bounded. Cross entropy loss is not immediately bounded, but you can, if you're assigning a label from 1,000 possibilities, you can guarantee that no label has 0 probability, and you can in fact bound the log loss. So it is possible, there are realistic settings where the log loss is bounded. So when we compare these, we're taking L to be the log loss, a bounded log loss in this case, and note how incredibly similar these are, right? This is just, when we did L2 regularization, there was a parameter in the Gaussian prior that ended up here, or actually sigma squared down here. What's happening is there's some unknown parameter in front of this log probability, or tunable, I should say. And these are both in some sense in strong agreement. So what's the difference here? The difference here is this is what's called a frequentist theorem. There's no assumption here that there's any truth in the prior. This is going to hold for an arbitrary programming language that defines this exponential distribution over all the programs in that programming language. There's no interpretation of that as any kind of true prior. Whereas this is making strong assumptions that the way the data was actually generated was by drawing your rule from your prior and then drawing your data from your rule. So the assumptions here behind this are much, in my opinion, much stronger. This is making no assumption that the prior is true. It's just a true fact about the programming language that this Occam guarantee holds. The prior there's no truth in the prior. Okay, so I'm going to prove it. And I think this is 3 slides. 20 years ago, I was doing a lot of research in learning theory. And Michael Kearns, a colleague at AT&T, was also working in the area. And he would often say that learning theory is all the theorems that sort of follow from combining Chernoff bounds and union bounds. And there's a lot of truth in that statement. This theorem is certainly something that just follows by combining Chernoff bounds and union bounds. So what's a Chernoff bound? A Chernoff bound is a kind of formal theorem that's like the law of large numbers. So I'm going to look at this second line first. So this L hat is an average of a loss over n train draws of training points. So you can think of it, so the true loss is the true expectation over drawing things from the population of that loss. This is a sample of size n. So the question is, so the law of large numbers will say that a sample of size n will roughly be distributed as a Gaussian. If n is large, this is going to have a Gaussian distribution. And intuitively, if it's Gaussian, if it's distributed as a Gaussian, the probability that it's different from its mean by an amount epsilon. So this probability is the probability that this measurement over the draw of the training data differs from its expectation by an amount epsilon. And this theorem says that that probability goes down, like is bounded, is upper bounded by something that goes down like a Gaussian, right? So it's very closely related to the law of large numbers, that an average of a large number of random draws has a Gaussian distribution. So the Chernoff bound says, and this is a particular Chernoff bound called the relative Chernoff bound, the probability of being off by epsilon goes as e to the minus the number of training points, so it's getting sharper over time as you get more training points, of this epsilon squared, right? It's Gaussian, so it's e to the minus epsilon squared. And then there's this L max term, and there's twice the actual, so normally in a Gaussian, this would be twice sigma squared, right? That a Gaussian would be twice sigma squared, where that sigma is the variance of the random variable we're taking the mean of. It turns out that if I've got something bounded in an interval, the variance, if I've got a number bounded between 0 and 1, the variance is bounded by its mean. The variant, so this is really just a form of the law of large numbers, but you put this mean in here to take into account that the lower the mean is, the lower the variance is. Okay, so this is the Chernoff bound, the relative Chernoff bound, and I can design this epsilon such that this probability is less than or equal to my confidence parameter times the probability of h. And I designed, so this is the design of epsilon. It's just designed such that if I square it, note that this is a positive number. This negative log probability is a positive number. If I square it, divide by L, by 2L, and multiply by L max, and then and N, and then take e to the minus that, I get this. Okay, so I've designed epsilon such that this is true. Okay, so the probability, so I can restate it this way. The probability that this is less than or equal to this is less than or equal to this. So so this is saying that this condition, right, is actually saying that H violates, that H is too large, right? This is a case where the true loss is larger than the measured loss by this amount epsilon. So if this is true, our theorem is being falsified. So the probability that H falsifies our theorem, that H is a bad guy, that it's making the theorem false, is less than or equal to delta times the probability of H. So that's coming out of the Chernoff bound. Now there's this union bound. So we know that for any H, the probability that H violates our bound is this. Now, what's the probability that there exists an H that violates the bound? Well, there's this thing called the union bound. The union bound says the probability of A or B is less than or equal to the probability of A plus the probability of B. And that generalizes to say that the probability that there exists an H that violates the bound can be no larger than the sum over H of the probability that H violates the bound. And the probability that H violates the bound is no larger than this by this statement. So now we've done a Chernoff bound and a union bound. Everything is Chernoff bounds and union bounds. So, so the probability that there exists something that violates our bound is less than or equal to this sum. Well, this sum sums to delta, right? Because it's just delta times the sum over H of the probability of H. So that means that the probability that somebody violates our bound is just delta. Well, that means that with probability 1 minus delta, nobody violates our bound. And that's the theorem, right? Sorry, that's not quite the theorem yet. That's what we've proven now is that nobody is this statement, that L of H is less than or equal to L hat of H plus L max times our value of epsilon. So this is our value of epsilon. But the theorem doesn't have this square root in it. Okay, so now we've got to get rid of this square root, or somehow I want to simplify this theorem. And this simplification is important because it makes this connection with the Bayesian algorithm very strong. So what's this simplification? It's really very simple. There's this general fact that the square root of AB is equal to the inf over lambda of this expression. This is related to the fact that the geometric mean is bounded by the arithmetic mean, or it follows from that. So now I can take this square root and an arbitrary lambda, since the square root is less than this expression for any lambda, I get this expression, right? So I've gotten rid of the square root by using this, sticking a lambda in. And now what I can do is I can take this L of H and pull it over here and solve for L of H, and I get this expression. Now this is almost the theorem that we wanted, the no free lunch theorem. But it's got this lambda in it, right? And this is true for all lambda. So what I've written here is actually stronger than the theorem I presented before, because the theorem I presented before is based on taking lambda equals 5. If I take lambda equals 5, this becomes 10 ninths, and I get a 5 here. But the point is that once lambda's 5, this is already 10 ninths, and this is not going to get any smaller as lambda. I mean, this is not going to get much better as lambda gets larger because it's already very close to 1. So there's sort of no point in taking lambda to be larger than 5, is the idea. And then it's more compelling, I think, in the first half of this unit to just stick those numbers in, so that you get an intuitive understanding of the implication of this, which is a little mysterious if I just stick lambda in there. So that's the theorem. Apologies for dragging you through the proof, but this is the way machine learning theory goes: turn off bounds and union bounds and some manipulation of square roots. Thank you.